You are standing inside a stone hall in Chang'an in 747 AD, and the summer heat outside is pushing past 100 degrees Fahrenheit. Sweat should be running down your neck. Instead, the air around you feels like a spring morning. No fans are spinning. No engine is humming. Water is running somewhere above your head, and that sound alone is dropping the temperature by 15 degrees. Emperor Xuanzong built this room to survive the worst heat of the year, and it worked without burning a single ounce of fuel. 200 years later, an entire nation knew how to build rooms like this. Today, almost nobody does. The physics never stopped working. Something else killed this technology. Once you see the exact mechanical failure point that ended it, you will understand why modern cities are hotter than they ever needed to be. Southern Chinese cities like Huizhou and Jiangnan packed thousands of wooden homes into narrow blocks. Streets ran only 6 to 8 feet wide. Every house shared a wall with its neighbour. This layout created a brutal fire hazard. One cooking accident could level an entire block of timber homes in under an hour. Builders fought this threat with a simple defence. They raised tall, windowless brick walls along every property line, called matukiang, or horsehead walls. These walls stood over 20 feet high and had 0 window openings. A fire could not jump easily from house to house because there was no wooden surface exposed on the sides. This defence created a second, deadlier problem. Sealing off every side wall meant sealing off every side window. Without side windows, a house had no way to catch a cross breeze. Summer heat had no exit route. Builders had solved the fire problem and accidentally built an oven. Master carpenters solved the airflow problem by looking straight up instead of sideways. They cut a narrow rectangular shaft through the centre of the roof, called a tianjing, or skywell. Picture a chimney sitting in the middle of a living room, except instead of smoke, it pulls out heat. A standard Huizhou skywell measured about 16 feet long and 8 feet wide, with a vertical drop of nearly 20 feet down to the ground floor. That narrow, deep shape is the entire trick. A narrow shaft speeds up airflow, the same way pinching a garden hose speeds up water. Here is the mechanical sequence. Morning sun hits the top of the shaft first. That sunlight heats the air sitting inside the upper section of the well. Heated air expands. Expanded air becomes lighter than the air around it. Lighter air rises and escapes straight out through the open roof gap. That escaping air leaves a gap behind it. Air pressure at the bottom of the shaft drops. Nature does not tolerate a pressure gap for long. Cooler air from the shaded ground floor, the covered walkways, and the damp storage rooms gets pulled upward to fill that space. This creates a continuous draft moving from the bottom of the house straight up and out the roof, running non-stop all day, without a single moving part. The house is now breathing on its own. But breathing air out of a hot room only removes heat that is already there. It does nothing to actively chill the new air rushing in to replace it. Builders still needed a way to attack the temperature of the incoming air itself. At the base of every skywell sat a shallow stone basin. Rainwater collected here and stayed pooled, along with standing water tanks built into the floor. Picture stepping out of a swimming pool on a windy day. The moment air hits your wet skin, you feel a chill, even if the air temperature itself is warm. That chill is a physical transfer of energy. Water sitting on a surface needs heat energy to turn into vapour. It pulls that heat directly out of the surrounding air to fuel the transformation. The air loses heat, and you feel cold. The skywell's rising draft pulled dry, warm air directly across the surface of that wet stone basin on its way up and out the roof. As the water evaporated off the stone, it stripped heat energy straight out of that passing air. Field measurements on real Huizhou homes recorded a drop of 4 to 8 degrees Fahrenheit compared to the outside air temperature, using nothing but standing water and a moving draft. This system had a hidden weakness. It only worked as long as that basin stayed full of water. Remove the water source and the entire cooling loop shuts down instantly, no matter how well the Skywell shaft was built. Air cooling handled the breeze moving through the house, but the outer walls still faced direct sunlight for hours every afternoon. Builders needed a wall material that could absorb that heat punch without letting it reach the inside. They fired local clay bricks inside sealed kilns at roughly 2,100 degrees Fahrenheit, then flooded the hot kiln chamber with water while sealing off the oxygen supply. Starving the fire of oxygen at that critical moment turned the red iron oxide inside the clay into blue ferrous oxide. This process also opened up thousands of tiny pores inside the brick, similar to the holes inside a kitchen sponge. These thick blue brick walls acted like a heat battery. During the hottest hours of the afternoon, the dense brick mass absorbed solar heat and held it, similar to how a cast iron skillet stays hot long after you turn off the stove. That stored heat took 8 to 12 hours to travel through the wall's thickness. By the time that stored heat reached the interior side of the wall, the sun had already gone down. The heat radiated harmlessly back out into the cool night air instead of cooking the room during the day. Those same microscopic pores absorbed moisture from humid night air, then released it slowly as the temperature climbed the next day, acting like a built-in humidity sponge. This wall system worked well for a private merchant home. An emperor with an unlimited treasury was not going to settle for passive brick and still airflow. He wanted a machine. In 747 AD, Emperor Xuanzong ordered his palace engineers to build the Liang Dian, or cool hall, inside the Chang'an Palace grounds. This was a fully mechanical, water-powered cooling machine built 200 years before anyone in Europe understood refrigeration. Palace engineers built a chain of water wheels that lifted cool pond water up into pipe networks running along the roofline. That water then poured down across the sloped roof tiles, forming a continuous sheet of falling water along every eave of the building. That falling water curtain hit two targets at once. First, it chilled the roof tiles themselves before the sun could bake heat into them, blocking that thermal energy from ever reaching the timber frame underneath. Second, as droplets fell past the open verandas, they evaporated in the open air, stripping heat out of every breeze that touched the building's exterior. The water did not stop working once it hit the ground. Cascading runoff flowed into channels beneath the floorboards where it struck small wooden paddle wheels. Those paddle wheels turned mechanical fan blades connected by simple gear shafts, physically blowing cooled air upward into the imperial seating platforms above. This was a fully automated self-powered air conditioning unit running entirely on gravity and moving water, with zero electricity and zero manual labour visible to the guests inside. Private estates could never afford this scale of hydraulic engineering. Wealthy merchant families still wanted a taste of the same imperial chill inside their own homes, and they found a clever way to fake it using nothing but stone and dirt. Elite Huizhou Manses buried a network of stone ducts several feet underground, running from the exterior courtyard directly into the interior walls. Each duct ended inside the living room through a carved stone dragon head, mounted at about waist height on the wall. Underground soil stays remarkably stable in temperature even when the surface air above ground swings from freezing to scorching. A few feet down, soil temperature barely moves, holding steady in the mid-60s year-round, similar to why a root cellar always feels cool no matter the season outside. The Skywell shaft above was still running its suction draft, constantly pulling replacement air into the house from somewhere. Builders gave that draft an underground shortcut. Instead of only pulling warm air from the courtyard, the draft also pulled air directly through the buried stone ducts. As that air travelled through several feet of cool subsoil, it dropped to a stable temperature near 61 degrees Fahrenheit before it ever reached the dragonhead vent and entered the living room. This underground trick pushed passive cooling almost as far as stone and dirt could take it. Every mechanism so far, from the skywell to the water curtain to the buried ducts, had been perfected and standardized across the empire by the year 1103. None of these systems came from China acting alone. Trade caravans moving along the Silk Road carried more than silk and spices. They carried engineering ideas between three completely different climate zones, and each civilization solved the same heat problem with a completely different physical trick based on what their local landscape gave them. Persian builders lived in open desert regions with strong, steady, high-altitude winds. They built tall wind-catcher towers called badgirs that stood high above the rooftops, physically scooping fast desert wind and forcing it down into the living space below. Their system depended entirely on the wind actually blowing outside. Indian builders in dry inland regions dug straight down instead of building up. They excavated multi-story stepwells called baolis, bringing living space into direct contact with deep, cool earth and underground water pools far below the scorching surface. Chinese builders in dense, humid southern cities could not rely on steady wind, and they did not have room to dig wide stepwells between shared walls. They built the internal stack effect skywell instead, a system that generates its own airflow using heat and pressure alone, completely independent of outside wind conditions. Song Dynasty official Li Jai collected these standards into a single technical manual in the year 1103, called the Yingzhou Fashi. This book locked in the exact shaft ratios, roof angles, and wall thicknesses that made passive cooling reliable and repeatable across the entire empire for the next 800 years. For 800 years, this system did not need a single upgrade. Then, within the span of one human lifetime, builders abandoned it completely. After 1949, national planners needed housing built fast, cheap and identical to shelter a rapidly growing urban population. They imported Soviet-style construction blueprints designed for cold Russian cities, not humid Chinese summers. These blueprints called for flat-roofed, poured concrete apartment blocks stacked in uniform rows. A concrete panel building goes up in a fraction of the time it takes to hand-carve timber brackets and cut a precise vertical skywell shaft through multiple floors. Timber framing vanished from these projects. Wide roof eaves vanished too, since they added no structural value to a concrete slab design. The skywell itself, the entire engine driving natural airflow, got left out of the blueprint entirely because it simply was not part of the standardized Soviet housing template being copied. Millions of families moved into these new concrete blocks over the following decades. Each unit was sealed, boxy, and completely dependent on outside power for comfort. Housing shortages alone did not finish off the skywell. The real killing blow came from a financial calculation made by real estate developers 30 years later. Economic reforms in 1978 opened Chinese cities to private land development at a massive scale. Urban land suddenly carried enormous financial value, and developers were charged with squeezing maximum income out of every single square foot of a construction site. Developers measured a building's value using a formula called floor area ratio, or FAR, which compares total rentable square footage against the size of the land parcel. Every square foot of rentable space directly increased a building's sale price and rental income. Picture the traditional skywell sitting in the middle of a floor plan. It is an open rectangular gap running vertically through multiple stories, generating zero rentable square footage on every single floor it passes through. A 10-story building with an open skywell shaft loses an entire column of rentable apartments compared to a building with a solid concrete floor in that same spot. Under this financial formula, the skywell stopped being an engineering feature. It became a hole in the balance sheet. Developers filled these voids with solid flooring on every project, converting wasted airflow space into paying square footage. The centuries-old thermal engine was erased for a spreadsheet calculation, not a physics failure. Even the developers who still wanted to preserve a courtyard well ran into a second, unrelated infrastructure change hitting cities at the exact same time. Through the 1990s, municipal water authorities extended pressurised tap water pipelines into rural counties and expanding suburban districts at a rapid pace. Families no longer needed a private courtyard well, a rain cistern, or a stone drainage channel to access clean water for daily use. Homeowners saw an old, wet-stone courtyard basin as an outdated liability once running tap water reached their kitchen faucet. Standing water attracted mosquitoes, required manual cleaning, and served no obvious modern purpose to a family with piped-in water. Across entire neighbourhoods, families paved over these old courtyard basins with solid concrete slabs. Remember the evaporative cooling loop from Chapter 3. That entire mechanism depended on a wet stone surface sitting directly in the path of the skywell's rising draft. Concrete does not evaporate. Pour a slab over that basin, and the phase change cooling effect driving 4 to 8 degrees of temperature, drop disappears permanently, even in a home where the skywell shaft itself was never touched. Two unrelated infrastructure decisions, one driven by real estate financing and one driven by public utility expansion, had now dismantled both halves of the ancient cooling system within the same 20-year window. Sealed concrete boxes with no airflow and no evaporative cooling needed a new solution fast, and one had just become cheap enough for every household to afford. Mass-produced electric split unit air conditioners dropped sharply in price through the 1980s and 1990s, becoming an affordable appliance for millions of urban households almost overnight. A split unit system solves overheating through brute mechanical force instead of passive design. A compressor squeezes refrigerant gas into a hot, high-pressure liquid. That liquid travels to an indoor coil where it expands rapidly and absorbs heat directly out of the room's air, using electrical power to run the compressor at every single stage of that cycle. This solution worked immediately, and it required zero changes to the building's core structure. Builders no longer needed a precisely angled skywell shaft, a stone evaporation basin, or thick blue brick walls. They only needed an electrical outlet and a hole drilled through a concrete wall for the exhaust unit. Passive cooling architecture essentially disappeared from new Chinese construction within 2 generations. Air conditioning units now draw close to 10% of all electricity consumed on the entire planet, and that number keeps climbing every summer as global temperatures rise. Power grids across major cities now buckle under peak summer demand, forcing engineers to search for an alternative that does not require burning more electricity to survive the heat. In November of 2023, researchers at Southeast University published new findings in the journal Science, detailing a ceramic material built from alumina and silica that cools a building's surface without using any electricity at all. This ceramic works through radiative cooling. The material reflects incoming sunlight away from the roof surface while simultaneously releasing the building's internal heat directly into outer space, passing through a narrow atmospheric window between 8 and 13 microns of infrared wavelength. Lab testing recorded a 26.8% reduction in total air conditioning electricity use on buildings using this roofing material. Architects have also started reintroducing full vertical skywell shafts into modern commercial towers. An 18-story office building in Jinan now uses a central multi-story ventilation shaft modelled directly on Ming Dynasty residential proportions to drive natural stack effect airflow through the entire structure and cut its mechanical cooling load. The exact same physics that chilled Emperor Xuanzong's palace hall in 747 AD is now sitting inside a modern steel and glass office tower, engineered from a completely different set of materials. Ancient builders never lost the argument on physics. They lost the argument on financial paperwork and pipeline infrastructure. Today's engineers are simply picking the old blueprint back up because the grid is finally showing the strain that the skywell was built to prevent in the first place.